All right, now that hopefully you have an understanding of kind of the terminology, we're going to get back into more of the mathematical computational physics as opposed to the conceptual stuff. Um, this is 17.1. We'll label it. It is looking at those things that we talked about with potential energy, potential difference, but looking at them more from an analytic, from a mathematical standpoint, and looking at the calculations and the equations. Again, at the core, at the foundation of this, you have to understand the differences between those terms and what they're asking for. That's the biggest thing here. Again, what we're trying to transition from is, all right, I have this charge at this location, it's sitting here, big deal. Now I'm looking at how much stored up energy that object has. And eventually the next phase will be releasing it. So we'll be looking at potential kinetic and things moving, flowing, and is what electricity is. So again, what we're going to be doing is looking more at taking a look at that conceptual stuff that I went over in the last two videos and looking at the equations, the calculations, and how we apply this. So you see these targets, and you'll see me kind of fly through a few of these slides because I kind of covered them just in a different format on the last two videos. Distinguish between electric potential energy, electric potential difference. And here's kind of the new things, looking at actually solving the problems using these things. Um, Eventually, the next phase will then be looking into batteries, and we'll get into that idea of voltage and start getting into voltage and current and electricity. So electric potential energy, there you have the key, you have the term thrown on there, energy. Here we're truly looking at how many joules that has, how many joules of energy it has to do work. That's no different than the Newtonian physics that we did. We're literally looking at this situation, how much stored up energy. So potential, stored up energy, you're dealing with the joules, and you change anything in that situation, it's going to change this value. And that's why we don't use it a whole lot per se until the very end. But that's what you're used to dealing with MGH and gravitational. Now we just deal with it in terms of electrical. Now, in electrical, we tend to look at the difference between location one and location two because it's not always falling to like a rock falling to the ground. So we have to look more at the change in potential energy, which is still going to be measured in joules. Okay. Just as a side note here, and this will play more into later, we can add that into our conservation of energy. Total mechanical energy stays the same. We had kinetic energy, 1/2 mv squared, gravitational, mgh, 1/2 kx squared if you have elastic. And now I have this another type of potential energy with the stored electrical energy. But the total is going to stay the same. The electric potential energy is going to be based on some things, how much charge you has, how much, or the strength of that electric field. And then we're going to look at moving it from point A to point B with the field against the field. And that's what we talked about with that analogy of dropping a rock, lifting it, going against the field lines in gravity, and dropping it, going with the field lines. So again, just as a review, again, field lines are always drawn in reference to a positive test charge. So if I was going from A to B, that's where it would want to go. It's going with the field lines. I would be dropping its potential energy. If I went from location B to A, it doesn't want to go there. I'd be increasing the amount of potential energy in that system, at least electrical. The main equation we're going to use is this one. Again, notice the delta, the change in. I'm going to be looking at the charge that I'm putting in to this external field, and I'm going to be multiplying it by the distance that I move it. Okay, from point A to point B, if that's 5 meters, that's what I would be putting in there. Now, just as a side note for some units here, your potential energy is still going to be measured in joules. This has to be in coulombs. Okay, your distance has to be in meters. Now, electric field can be in a couple of different formats, and we'll talk about it here in a few minutes. But the main format at this point, because when we did electric field, it was the force per charge. So you're dealing with newtons per coulomb. Okay, we're going to have a slightly different unit that we can also use here in a few minutes. Positives and negatives. Okay, and this will come into play more later. But the negative sign indicates that the electric potential energy will increase if the charge is negative and decrease if the charge is positive. What does that mean? Again, these field lines are drawn with a positive test charge. Okay, so if you use a positive charge, you're going to see it drop if it goes with the field lines. You're going to see it increase if it goes. Now, if this were a negative, it would be the opposite. If you put a negative charge in here and you went with the field lines, you would be, so if I went from A to B for this negative charge, if I go from A to B, that's not where this electric negative charge wants to go. Because remember, these are drawn for positives. So in this case, you would actually be increasing the amount of potential energy. If you went from B, let's say you go B back to A for the negative charge, okay, you'd be going against the field lines. Well, that's where the negative charge wants to go. You'd be decreasing it. So you have to keep that in mind. That's kind of the first time you've seen this opposite. The field lines apply to a positive test charge. If you throw in a negative, you're going to have to kind of think opposite there. So change in potential energy, okay, your book doesn't put that in there. Just keep that in mind that it is a change in the potential energy electrical. It is negative QED, charge, the electric field strength, and the distance that it's moving. All right. Those slides were just going over, and again, you have the raw slides. Those slides were just going over what we did with the previous videos and looking at with the field lines and against the field lines. In electric, again, we talked about a more convenient way is to talk about the electric potential. Notice we've dropped the term energy. Okay. This is going to be more of a ratio and tell you the amount of joules per coulomb you have. So it's more applicable. I can throw in any different charges. What happens if I double the charge? I don't have to redo a whole bunch of calculations. I have a ratio that fits for that location, for that situation. Okay. Potential difference then. Potential difference. Notice it has that potential. So I'm still dealing with joules per coulomb, but now I'm looking in the difference from point A to point B. One format I can look at is the change in potential energy, okay, divided by charge, okay. Again, better to put this. So your potential is your potential energy divided by your charge. So once you know your potential energy, you can, and you know your charge, you can easily figure out the volts, the potential. The more convenient way is to find this potential difference, and there are a couple of different formats and different versions that we're going to look at here. So you have your change in potential energy, okay, divided by your charge. This is going to give you your joules per coulomb, which is very, very useful when we talk about finding a location and applying it to any given charge. So just as we talked about, the SI unit is the volt, Alessandro volta. Okay, 1 coulomb of charge moves through a potential difference of 1 volt. It's going to gain a one joule of energy. 2 coulombs of charge moves through a 1 volt. It's going to gain two. It's a ratio of joules per coulomb, and that's why it's so useful. Um, since it is an SI unit, you can see any of the metric prefixes, metric prefixes such, and you may see kilovolts, millivolts, whatever it might be. All right, some substitutions here. Just want to show you where some of these can come into play. So your potential energy electric is negative QED. If I sub that into that equation that I just showed you, okay, now notice what can cancel: your Q's. And you end up with this. Okay? You end up with another form of the potential difference, and this one's pretty useful as well. All right, I'm going to get to some problems here. Actually, let me go back 1 second to this last equation here. Talked about this is newtons per coulomb, typically is what you might see for electric field. Now, if you look at this format, okay, again, you have your electric field, you have distance, this is in meters. Another way you can write this, if I rearrange this, okay, remember, this is in volts, this is in meters. So another unit that represents the same way, and we can go into what a newton is and go and you'll find the derivation. It is also equivalent to volts per meter. Okay, so they are one and the same. So as you go forward, 1 volt per meter and 1 newton per coulomb, you're going to see them be equivalent units. So don't get thrown off if you see it in this format as well. All right. So let's look at some of these problems. The trickiest part about these problems is figuring out and keeping the term straight, and what are you actually trying to calculate? Are you trying to calculate potential energy? Are you trying to calculate the potential difference, the potential? What are you trying to calculate? That's going to be the trickiest part. This particle moves 10 meters. So I'm going to have a displacement, a distance change of 10 meters. I'm going to have an electric field strength of 75 newtons per coulomb. And I'm going to see an electric potential energy decrease. So a change in potential energy of negative 4.8 times 10 to the negative 16th joule. What is the particle's charge? Okay, so again, I'm looking at potential energy here. That's why I have PE. That's how I knew it was potential energy and not volts, or I'm sorry, potential difference, or potential and measured in volts. The other key was looking at the units as well. So if you look at some of your formulas, the easiest one to deal with is your change in potential energy is negative QED. They're going to want to rearrange that because you're going to solve for Q. I'll just do that straight out the gate here. Q, negative change in potential energy, all over the electric field strength times the distance. So you're going to have negative 4.8 times 10 to the negative 16th joules, all over the electric field strength, and multiplying it by the distance. Okay. Be careful with your parentheses. Okay. and the charge will come out to be in a positive charge, and it'll be 6.4 times 10 to the negative 19th coulomb. Again, the biggest thing here is identifying that you're dealing with potential energy and which equation to use. What is the potential difference? Okay, so potential difference. So I'm going to be looking at something with delta V, potential difference between the initial and final locations in of in in problem one. So I'm using the same problem, so I'm still in the same electric field. So 75 newtons per coulomb. I'm moving a distance of 10 meters. The easiest potential whoops, sorry, jumping ahead there with that. The potential difference is negative ED. So 75 times 10 and negative 750 volts. Now the negative positive on potential difference, just telling you if it's dropping or increasing based on if it's a positive charge or a negative charge. And we'll get more into that when we get into circuits. All right, electron. Oh, so first time I got a negative here. Moves 4.5 meters in the direction of an electric field. Okay. Now remember, the direction of the electric field lines is based off of a positive test charge. So Q is going to be negative 1.6 times 10 to the negative 19th coulomb. The distance it moves is 4.5 meters. And the electric field strength is going to be 325 newtons per coulomb. Determine the change in electric potential energy. So I'm dealing with joules, I'm dealing with change in potential energy. Now looking at what I have Q, I have E, and I have D. So that's the equation I want to use. So negative 1 point, because it's an electron, times 325 times 4.5 meters, and plug and chug, and you'll get a change in potential energy of 2.3 times 10 to the negative 16th joules. And it should make sense that you're increasing the potential energy, even though it's going with the field lines, because that's showing you how a positive test charge would want to go. So you got to think opposite for these electrons. All right, so we're going to start talking a little bit about batteries. We're going to get into them hardcore late in the next chapter here, but a battery is a storage device. Storage, thinking of potential energy. Okay, now there's a chemical reaction going on and some redox reactions, and we'll talk about that in later chapters. But if you look at a battery, it's measured in volts. The typical square one you stick your tongue to and get a little sour zap is a 9-volt battery. That's telling you the amount of potential difference. That's the amount of joules you have to do work between terminal A or negative and positive terminals. Most year-round batteries, whether it's AA, AAA, CD, are 1.5 volts. So it's telling you how much energy you have, the difference between point A and point B. So you got your typical 1.5 volt. Again, it could be a C, a D, it could be an A, or a AAA, a AA, whatever it might be. It's telling you the potential difference across its terminals. So the one terminal is 1.5 volts higher, or joules per coulomb higher than the other one. So just kind of notation here. So if we designate that the negative terminal of battery is at zero potential. So it's like when we did potential energy with the roller coasters, we said the lowest point, even though it might be slightly off the ground as our reference point, we use it as zero potential. The positive terminal would have a potential of 1.5 volts, which we could just as accordingly choose the potential being a negative 0.75 volts and positive 0.75 volts. That's still a difference of what? 1.5 volts. Let's just make we just make our lives easier, just like we did with the roller coasters or pendulum, and use the low point as our reference of zero. What's important is not this value, but the value that is the difference between terminal A and B, the negative and positive. So that's why I don't care that one might be 1 and one might be 10. What I care about is that the difference is 9 volts. All right. So the difference between change in potential energy and potential energy, the change, okay, it's dependent on charge and the distance away. If I just want to use my reference point as being zero, I can just simply exclude that and not care that one might be 0.75 and one might be negative 0.75. And so again, it just goes back to using our reference of using the negative as zero, or what you hear of as ground, and using the other one as the actual potential difference. And so they become one and the same. It makes our life a lot easier. Again, just think of the roller coaster and how we always pick the low point as our reference point. In a uniform electric field, remember, all that means is that what I've created is not crazy curved field lines. I've just created a system where all the field lines are nice in that area, nice and evenly spaced and parallel to each other. Okay? What's going to affect the electric potential energy? It's going to affect what charge you have, the field strength, and the distance between them. Okay, QED. This question just talking about mechanical energy and being conserved. Just remember, yes, I have kinetic energy. We will have it moving. And then you have all sorts of forms of potential energy. It could be anything from elastic, it could be gravitational, electrical. Okay. And what we do to make our life a little easier is ignore things like heat, friction, light, those types of things. Talking about our reference points again, we just make it easier. We just use the zero level to make things easier. So if we're dealing with just like our roller coaster, okay, even though the ground might be down here, my lowest point would be here. I use that as my reference point of zero. The same thing is true when we use batteries and different, and we talk about electrical systems. We use the negative terminal or the ground as literally as ground zero upon there, but use that as our zero. And it just makes our life a lot easier and the calculations simpler. So even, with the roller coaster might be off the ground a little bit. The roller coaster is not going any lower than that. So that's what we use as our zero potential energy, where our kinetic energy was max. All right, so let's take some problems here. Here's a lightning bolt. Okay. Electric potential energy in a lightning bolt. So potential energy is 35 coulombs of charge travels to the ground from a cloud that's 2 kilometers above. An electric field strength is measured, and that's a lot of what they're doing with when they're doing the lightning detection devices, especially with NASA. They start measuring the electric fields, and they know when the ionization of air can occur. So I have 35 coulombs of charge. That's a lot of charge. I have a distance from the ground to the zero of 2 kilometers. Okay, I got to be careful of that. Got to make sure I convert that into meters. Okay, so you're dealing with 2,000 meters there. I also know the electric field strength when this is going to occur is 1 times 10 to the 6 newtons per coulomb. That's a lot of force. And it wants to know the electric potential energy. So negative QED. So I have Q is 35. I have my E is 1 times 10 to the 6th. And I have my D is 2,000 meters. Make sure you've converted that to meters. Okay. And you plug and chug, and you should get negative 7 times 10 to the 10th joules. A lot of energy to do work. All right, if you ever used a spark plug or you go and change the spark plug, it always tells you to set for a, especially with like small engines, it always tells you to measure the gap between the electrodes. And that's important because that's spacing. And so your distance is different, and that distance has to be very specific to that engine to create the spark, which then ignites the gasoline, creating the combustion reaction in the chamber. If the gap is too big, the potential energy is dropped way down and your electric field strength is way down. So if it's too close, then you're getting too early of a spark. So the gap between the electrodes and a spark plug, in this specific case, is going to be 0.06 centimeters, which is an issue, centimeters. You got to make sure that's in meters. The electric field strength is set up by that battery is 3 times 10 to the 6 volts per meter. So again, that's just the other units. It's the same as newtons per coulomb. Just showed you the different way earlier to calculate that. So it wants to know what potential difference. In other words, what size battery would you need to hook this up to get this thing to arc and to spark? So negative ED. So you have 3 times 10 to the 6th volts per meter. That's your E. Negative sign out here. And your distance is going to be 0.06 times 10 to the negative 2. And 1.8 times 10 to the 3rd volts. And the last problem here, 2 parts here, A and B. We're going to look at potential difference and potential energy. So looking at the same system, just looking at calculating some different variables here. Again, showing you, making kind of reinforcing the idea you have to understand and make sure you understand the difference between potential difference and potential energy. A proton. So I have a charge of a proton, 1.6 times 10 to the negative 19th coulomb, is at rest in a uniform electric field with a magnitude. Okay, so there's my electric field. The proton is displaced, so there's my distance. And as a result, find the potential difference between the proton's initial and final. So we're using the initial and final, reference is 0. So potential difference, the form that we have that we should probably use is because I have the electric field, I have the distance. There's my electric field, 8 times 10 to the 4th. And the displacement is 0.5. So you get negative 4 times 10 to the 4th volts. And remember, that is the amount of joules per coulomb that you have available. Find the charge in the electric, change in the electric potential energy. So potential energy, negative QED. So you'll have your negative 1.6 times 10 to the negative 19th. You have your electric field strength, which was 8 times 10 to the 4th. And you have your distance of 0.5. And you get negative 6.4 times 10 to the negative 15th joules of energy available to you. All right. So again, Big things are is you got a lot of new equations with terminology. You have to make sure you understand the difference between, if I'm talking about the change in the actual potential energy, look for that keyword energy. That tells you you're dealing with straight up joules. Or if you're dealing with like the potential difference or the potential and you're dealing with volts, okay, which is joules per coulomb. It's that ratio. All right. Again, make sure you reach out to me if you need some help or if we need to have a Zoom meeting or meet up. Also be putting out a couple of practice problems just for you to practice on your own with this. But again, this is kind of the foundation for circuits, and you're starting to see this like term of volts. And a lot of you have seen that when we talked about with batteries, and we'll continue looking at that. We have things moving. So the next phase, just like when we did Newtonian physics, we went from potential energy to kinetic energy. We're going to be doing the same thing here, except for now when we start talking about kinetic energy with charge, we're actually talking about the current or electricity in circuits.